Astronomers analyzing data from the interstellar object 3I Atlas have detected highly collimated radiation beams extending over distances of more than 1 million kilometers, rays that should have been blurred by the object's rotation but remain tightly focused into parallel streams. This contradicts every model of cometary outgassing and rotational dynamics, leaving scientists at Harvard University, Oxford, and the Vega Observatory in Novosibirsk profoundly unsettled. The image captured on November 9, 2025 shows something that shouldn't exist, according to conventional astrophysics. When comets approach the sun, they release gas and dust in asymmetric jets that cause them to tumble and spin. That rotation should smear any radiation into diffuse clouds. Instead, 3I Atlas produces beams so precise they appear engineered, maintaining coherence across distances equivalent to roughly 2.5 times the Earth-Moon separation. No natural process in cometary science explains this level of collimation. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University, has been studying the object's behavior since its detection. His observations have only deepened the puzzle. Writing in his research blog, Loeb noted that the collimated rays should have been blurred due to rotation, yet they remain sharply defined. The implication hangs in the data like a question mark. Either the object isn't rotating the way comets should, or something about its structure is fundamentally different from every Tsabi icy body previously observed. Unlike typical comets, which are essentially dirty snowballs held together by frozen volatiles, 3I Atlas survived its close approach to the Sun without fragmenting. Most comets that venture near our star experience catastrophic structural failure. The heat vaporizes their ices unevenly, creating stress fractures that rip them apart. Comet Shoemaker. Levy 9 broke into more than 20 fragments before colliding with Jupiter. Comet Ison disintegrated entirely during its 2013 perihelion passage. Yet 3I Atlas, despite enduring similar thermal stress, remained intact as a single coherent object. If you're finding this as fascinating as I am, consider subscribing to the channel and hitting that like button. It really helps us bring more of these mind-bending cosmic mysteries to you. That resilience is statistically improbable for a natural comet. Loeb has stated explicitly that the object's structural integrity indicates an artificial origin. The word artificial carries enormous weight in astronomical discourse. It suggests design. It suggests engineering. It suggests intelligence operating on scales of time and space that dwarf human civilization. Before dismissing this as speculation, consider the numbers. The object maintained structural cohesion under thermal loads that would vaporize and shatter natural cometary material. It produces radiation patterns that defy rotational physics. And according to trajectory analysis conducted by Igor Maslov, an engineer at Novosibirsk State University's Vega Observatory, it arrived from a region of the Milky Way that shouldn't be producing fresh comets at all. Maslov's calculations indicate that 3I Atlas was likely ejected into interstellar space by a powerful gravitational disturbance, possibly a close encounter with a massive planet or a stellar flyby. Such events are common enough in young star systems, where planetary orbits haven't stabilized, and stellar siblings still cluster in formation groups. But those conditions existed billions of years ago. The object is arriving now, from the thick disk of the galaxy, where old stars drift in ancient orbits. British astronomer Matthew Hopkins from the University of Oxford has attempted to quantify exactly how old this wanderer might be. Using a statistical model that analyzes the object's velocity vector and trajectory against the known structure and age distribution of the Milky Way, Hopkins calculated that with 68% probability, 3I Atlas is between 7.6 and 14 billion years old. Think about what that means. The universe itself is only 13.8 billion years old. Our solar system formed 4.5 billion years ago. If Hopkins' upper estimate is correct, this object predates Earth, the Sun, and every planet orbiting our star. It may have formed when the galaxy was young, when the first generation of metal-rich stars began condensing from primordial gas clouds. All non-interstellar comets, such as Halley's Comet, formed inside the solar system, so they are no older than 4.5 billion years, Hopkins explained in his analysis. But interstellar wanderers can be much older, and for those we know, our statistical method suggests that 3I Atlas is very likely the oldest comet of all known. Stop and consider that. Halley's Comet, which has been observed for more than 2 millennia and appears in historical records from ancient China, Babylon, and medieval Europe, is a relative infant compared to this object. The oldest rocks on Earth, zircon crystals from Western Australia, date to about 4.4 billion years. 3I Atlas may be 3 times older than the oldest terrestrial matter ever discovered. It carries information from an epoch when the Milky Way was still settling into its current structure, when star formation rates were dramatically higher, when the chemical composition of interstellar gas was fundamentally different. Now about the data. The collimated radiation observed from 3I Atlas extends more than 1 million kilometers into space. To grasp that scale, imagine standing in Los Angeles and seeing a laser beam so tightly focused it remains visible and coherent all the way past the moon and continuing for another 700,000 kilometers beyond. That's the level of precision being observed. Natural processes, gas jets, particle streams, magnetic field interactions, don't produce that kind of collimation without some form of focusing mechanism. In plasma physics, certain configurations of magnetic fields can channel charged particles into narrow beams. Active galactic nuclei produce jets that remain collimated across thousands of light years, but those structures are powered by supermassive black holes accreting matter at relativistic speeds. Pulsars emit beams of radiation focused by magnetic fields billions of times stronger than anything found in the solar system. But a comet? A comet shouldn't have the magnetic infrastructure or energy budget to maintain beam coherence over 1 million kilometers. Loeb has been careful to note that conventional explanations fail on multiple levels. Gas outflows from comets are inherently asymmetric, different areas of the surface heat at different rates, causing jets to fire in various directions. This asymmetry generates torque, which increases rotational velocity. The faster an object spins, the more any linear features, like jets or radiation beams, should blur into circular patterns when viewed from a distance. Yet the November 9th images show no such blurring. The rays remain parallel and distinct. It is unlikely that gas outflows slowed the object's rotation, Loeb wrote. On the contrary, asymmetry in the process of gas release usually leads to increased rotation. Read between the lines. If gas outflows didn't slow the rotation, and natural processes should have increased it, then either the object's rotation has been artificially stabilized, or its structure is so radically different from conventional comets that standard physics doesn't apply. Neither option fits comfortably within established science. Here's where things get strange. The scenario that makes the most sense from a purely mechanical standpoint is also the one that challenges fundamental assumptions about the prevalence and longevity of technological civilizations. If 3I Atlas is indeed artificial, if it was constructed rather than accreted from primordial ice and dust, then it represents technology operating on timescales that exceed the entire history of complex life on Earth by a factor of 2 or 3. Consider the engineering challenge. To build an object capable of surviving interstellar transit for billions of years requires materials that don't degrade under cosmic ray bombardment, doesn't fracture under thermal cycling between near absolute zero and solar heating, and doesn't succumb to micrometeorite erosion. The object would need to be constructed from something far more resilient than water ice and silicate dust. Perhaps metallic hydrogen, stable at high pressures. Perhaps exotic forms of carbon, fullerenes or nanotubes arranged in fractal lattices. Perhaps materials entirely unknown to current science. And it would need power. If the collimated beams are intentional, if they serve some function rather than being accidental byproducts, then the object must have an energy source that remains active after billions of years in the void. Radioisotope thermoelectric generators, the technology that powers Voyager and New Horizons, degrade on timescales of decades. Fission reactors consume fuel. Fusion requires maintenance. What power source operates reliably for 10 billion years? The alternative explanation is equally troubling. If 3I Atlas is natural, then there exist cometary formation processes and structural dynamics that current planetary science has completely failed to anticipate. It would mean that objects from the thick disk of the galaxy, ancient metal-poor regions where star formation has been dormant for billions of years, can somehow produce icy bodies with material properties superior to anything formed in younger systems. It would mean that the standard model of comet composition, based on decades of observation and sample return missions, is fundamentally incomplete. Matthew Hopkins' statistical model provides a framework for understanding where the object originated, but it doesn't explain what it is. The thick disk of the Milky Way contains stars with ages ranging from 8 to 10 billion years, formed during an earlier epoch of galactic evolution, when the metallicity, the abundance of elements heavier than helium, was significantly lower than today. Planets and comets forming around those ancient stars would have different chemical compositions: less iron, less silicon, more hydrogen and helium. In theory, such objects should be weaker, more volatile rich, more prone to fragmentation. Yet 3I Atlas is stronger. It survived. It persists. Hopkins noted that the discovery provided a fantastic opportunity to test our model on something new, and likely ancient. The model had been developed using theoretical frameworks and simulations, waiting for real data. Now the data exists, and it confirms the theoretical prediction. Interstellar objects can indeed be far older than anything native to the solar system. But confirmation raises new questions. If one ancient wanderer has arrived, how many others are passing through undetected? How many relics from the early galaxy are currently drifting through the space between stars, invisible until they happen to pass close enough to the sun for reflected light or outgassing to reveal their presence? The detection of interstellar objects is still in its infancy. Oumuamua, discovered in 2017, was the first confirmed visitor from beyond the solar system. Its elongated shape and unexpected acceleration as it departed sparked intense debate. Some astronomers attributed the acceleration to cometary outgassing, despite the absence of a visible coma. Loeb suggested it might be a light sail, a thin reflective structure propelled by radiation pressure. The controversy hasn't been resolved because Oumuamua is now too distant and faint to study further. Then came 2I Borisov in 2019, a more conventional-looking comet with a clear coma and tail, displaying spectroscopic signatures consistent with known cometary ices. Its behavior matched predictions, and the astronomical community largely treated it as confirmation that interstellar comets are, fundamentally, similar to their solar system counterparts. That assumption is now under severe pressure. 3I Atlas doesn't fit the pattern. It doesn't fragment. It doesn't blur. It produces radiation beams that remain collimated across scales, where collimation shouldn't be possible. And it may be older than the continents, older than the oceans, older than the very rocks beneath our feet. Think about what that means for the search for extraterrestrial intelligence. The field has historically focused on detecting radio signals or optical pulses, deliberate transmissions sent by civilizations attempting to communicate. But if technological artifacts can survive for billions of years, drifting silently through the galaxy, then perhaps the majority of evidence for alien intelligence isn't signals at all, Perhaps it's hardware, ancient probes, derelict vessels, monuments to civilizations that rose, flourished, and vanished before Earth's sun ignited. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete absence of evidence for them, takes on new dimensions if the evidence is physical rather than electromagnetic. Radio signals degrade. They disperse across interstellar distances, becoming indistinguishable from noise. But matter persists. A well-designed object, built from stable materials and placed in a trajectory that avoids stellar collisions, could theoretically survive until the stars themselves burn out. Is 3I Atlas such an object? The data remains inconclusive, but the hypothesis is no longer dismissible. Loeb's credibility, though controversial in some circles, is backed by decades of peer-reviewed research on black holes, cosmic inflation, and the high redshift universe. Hopkins is a respected statistical astronomer whose models have been validated by subsequent observations. Maslow's trajectory analysis is grounded in orbital mechanics that have been refined over centuries. These aren't fringe voices. They are serious scientists confronting data that doesn't fit. The next phase of investigation will depend on instruments that don't yet exist or aren't yet operational. The Vera C. Rubin Observatory in Chile, scheduled to begin its legacy survey of space and time in May 2025, will detect thousands of interstellar objects over the next decade. Its wide-field camera will photograph the entire visible sky every few nights, identifying transient and moving objects with unprecedented efficiency. If 3I Atlas is part of a larger population of ancient wanderers, Rubin will find them. The James Webb Space Telescope, already operational, could potentially observe 3I Atlas in infrared wavelengths, detecting thermal signatures that reveal surface composition and internal structure. Spectroscopic analysis might identify absorption lines from exotic compounds, materials that don't occur naturally in typical cometary environments. If the object is metallic, or if it contains crystalline structures inconsistent with ice, Webb could provide the definitive evidence. Ground-based radar observations, similar to those used to study near-Earth asteroids, might map the object's shape and surface texture in high resolution. Radar can penetrate thin dust layers and detect subsurface features. If 3I Atlas has internal cavities, or if its density distribution is anomalous, radar would reveal it. The Arecibo Observatory, which conducted many such studies, collapsed in 2020. But the Deep Space Network and the Green Bank Telescope remain operational, and both are capable of planetary radar astronomy. There is also the possibility of a direct mission. Spacecraft have previously rendezvoused with comets. ESA's Rosetta mission orbited 67P Churyumov-Gerasimenko and deployed a lander to its surface. NASA's Stardust mission collected samples from Comet Wild 2 and returned them to Earth. A mission to 3I Atlas would be vastly more difficult. The object is traveling at high velocity relative to the solar system, and intercepting it would require enormous amounts of propellant. Current chemical rockets couldn't match its trajectory. Nuclear propulsion, ion drives, or gravity assists from multiple planets might make it feasible, but the mission would take decades to plan and execute. Yet the scientific return could be transformative. Physical samples from an object potentially 10 billion years old would rewrite cosmochemistry. If the material contains isotopic ratios inconsistent with solar system formation, it would confirm an extrasolar origin. If the structure shows signs of artificial processing, machine surfaces, geometric regularity, embedded technology, it would confirm intelligent design. Either result would be among the most significant discoveries in the history of science. For now, the investigation continues at the level of telescopic observation and theoretical modeling. Astronomers worldwide are monitoring 3I Atlas as it moves through the inner solar system. Photometric data will reveal whether its brightness varies in patterns consistent with rotation. Spectroscopy will identify molecular emissions from its surface. Polarimetry might detect alignments in reflected light that indicate magnetic fields or structured surfaces. But time is limited. Interstellar objects pass through quickly. Oumuamua was observable for only a few weeks before it faded beyond detection limits. 2I Borisov remained visible for several months, but its window closed as it receded into the outer solar system. 3I Atlas, moving at velocities typical of objects from the thick disk, will eventually accelerate beyond the reach of even the most powerful telescopes. The opportunity to study it is finite. What happens if the data continues to defy conventional interpretation? If subsequent observations confirm that the collimated beams persist without rotational blurring? If spectroscopic analysis reveals surface materials inconsistent with natural accretion? If the object's trajectory, when traced backward through galactic dynamics, points to a star system that existed 12 billion years ago in an era when planets were just beginning to form around metal-poor stars, the scientific community would face a paradigm shift comparable to the Copernican revolution. The assumption that Earth is the only world with advanced life, or even that technological civilizations are rare and short-lived, would crumble. The galaxy would be revealed as an archaeological site, a vast museum containing the remnants of countless cultures that rose and fell across deep time. Humanity's place in that continuum would be that of newcomers, late arrivals, in a cosmos already ancient when our sun was born. Loeb has argued for years that the search for extraterrestrial intelligence should expand beyond radio signals to include physical artifacts. His Galileo project, launched in 2021, aims to use astronomical instruments to detect anomalous objects in Earth's vicinity. The project's methodology emphasizes data transparency and scientific rigor, applying the same standards used in mainstream astronomy to phenomena often dismissed as unworthy of serious study. 3I Atlas provides a test case. If the object is natural, understanding it will require new physics, new models of cometary structure, new theories of material behavior under extreme age and radiation exposure, new explanations for beam collimation in low-density environments. If the object is artificial, understanding it will require confronting the possibility that intelligence is not rare, that civilizations can endure for billions of years, and that the universe is populated by relics we've been too narrow-minded to recognize. Hopkins's age estimate, if accurate, places the object's formation in the epoch when the Milky Way's thick disk was assembling. Star formation in that region peaked between 8 and 10 billion years ago, then declined as gas supplies were exhausted or expelled by supernova winds. The stars that remain are old, metal-poor, and widely dispersed. If 3I Atlas formed during that era, it witnessed the galaxy's maturation. It drifted through the plane of the disk, possibly passing near thousands of star systems before gravitational perturbations sent it on a trajectory that intersected with the solar system in late 2025. The probability of such an intersection is extraordinarily low. The galaxy is vast, roughly 100,000 light-years in diameter, with stars separated by light-years of emptiness. For an object to travel from the thick disk across billions of years and trillions of kilometers and happen to pass within detectable range of Earth requires either remarkable coincidence or deliberate targeting. Coincidence is statistically plausible if interstellar objects are common. Estimates based on the detection rate of Oumuamua and 2I Borisov suggest that, at any given moment, there may be thousands of interstellar objects within the orbit of Neptune. Most are too small or too distant to detect. But if that population includes a significant fraction of ancient wanderers from the thick disk, then 3I Atlas might simply be the first one humanity's technology has been capable of identifying. Deliberate targeting is a more provocative hypothesis, but not one that can be dismissed without evidence. If the object is artificial, and if it was designed to survey star systems, then its trajectory might have been planned. The thick disk, with its high metallicity stars and stable orbits, would be an ideal region for long-term observation platforms. An automated probe launched billions of years ago could still be executing its mission, visiting star after star, collecting data, transmitting reports to a homeworld that may no longer exist. There is a melancholy beauty to that scenario. A machine, built by a civilization that flourished when the universe was young, continuing its work long after its creators have vanished. It drifts through the darkness, alone and purposeful, carrying out instructions encoded in systems too robust to fail. It approaches the sun, scans the planets, records the presence of an industrial civilization on the third world from the star. And then it departs, accelerating into interstellar space, space, bound for the next target on a list compiled eons ago. If such a probe exists, what would it tell its makers about us? That we are young, barely a century into the use of radio technology. That we are fragile, confined to a single planet with no permanent presence beyond low Earth orbit. That we are curious, building telescopes and space missions despite enormous costs and uncertain returns. That we are beginning to look outward, to ask whether we are alone, to wonder what lies beyond the boundaries of our small system. And what would we learn from it? The engineering principles required to build something that survives for 10 billion years. The physics of propulsion and power generation on timescales that dwarf human history. The materials, science of substances that don't corrode, don't decay, don't fail. The information architecture of systems that store and process data across geological epochs. Every component would be a revelation. Every subsystem a window into technologies far beyond current human capability. But recovery is a distant dream. The object is already receding. Within months, it will pass beyond the orbit of Mars, continuing outward toward the outer planets and the heliopause. Short of a crash program to design, build, and launch an interceptor, something requiring international cooperation, vast funding, and technological breakthroughs in propulsion, 3I Atlas will escape unexamined. That frustration is familiar to astronomers who study transient phenomena. Supernovae, gamma-ray bursts, fast radio bursts, events that last seconds or days, offering brief glimpses of extreme physics before fading forever. Interstellar objects are similar, except the timescale is weeks or months instead of seconds. The universe presents a puzzle, tantalizing and profound, then withdraws it before the solution can be fully grasped. Yet even incomplete data can be transformative. The November 9th image, with its inexplicably collimated beams, has already altered the conversation. Before that observation, 3I Atlas was interesting but not paradigm-threatening. It was an old comet from the thick disk, valuable for cosmochemical studies, but not fundamentally mysterious. The collimated radiation changed everything. It introduced an anomaly that demands explanation, and no explanation currently fits. Loeb's suggestion of artificial origin is the most direct interpretation, but it carries implications that most scientists are reluctant to embrace. The burden of proof for extraordinary claims is high, and rightly so. False positives in the search for extraterrestrial intelligence, pulsars initially thought to be alien beacons, fast radio bursts misinterpreted as deliberate signals, have taught the field caution. Declaring an object artificial without overwhelming evidence would invite ridicule and damage credibility. But caution can become paralysis. If the threshold for accepting anomalous data is set too high, genuinely revolutionary discoveries might be dismissed as artifacts or errors. The history of science includes numerous examples of observations rejected because they didn't fit prevailing theories, only to be vindicated decades later. Continental drift, quasi-crystals, high-temperature superconductivity, all faced initial skepticism before becoming accepted fact. The radiation beams from 3I Atlas are not subtle. They are not marginal anomalies buried in noise, visible only after extensive statistical processing. They are clear, distinct features in high-quality images, observed by instruments with well-understood characteristics. Dismissing them requires proposing a mechanism that, while natural, is so unusual it has never been observed in any other comet. That's not impossible, but it's not simple either. Here's where the investigative pressure intensifies. If the beams are real, if they persist in subsequent observations, and cannot be explained by instrumental artifacts or processing errors, then the scientific community must confront a genuine mystery. The options narrow to three: unknown physics, unknown materials, or unknown origin. Unknown physics might involve exotic states of matter or field configurations that don't occur in typical cometary environments. Perhaps the object passed through a region of space with unusual properties, a dense molecular cloud, a supernova remnant, a stellar magnetosphere, that altered its structure in ways not previously documented. Perhaps interactions with cosmic rays over billions of years induced changes in its material lattice, creating domains that channel radiation preferentially. These scenarios are speculative, but not impossible. Unknown materials might involve substances that don't exist in the solar system's inventory of cometary ices and dusts. The thick disk, with its different metallicity and formation history, might produce compounds that are thermodynamically unstable in younger systems, but persist in older ones. Perhaps 3I Atlas contains phases of water ice that only form under extreme pressure and low temperature, maintained over billions of years by the object's journey through the interstellar medium. Perhaps it contains carbides or nitrides that don't sublime under solar heating, providing structural integrity that ordinary comets lack. Unknown origin is the hypothesis that Loeb advocates. If the object was constructed, then its properties don't need to fit natural models. Beam collimation could be intentional, achieved through apertures or lenses designed for that purpose. Structural strength could be engineered, using materials selected for durability rather than cosmic abundance. The lack of rotational blurring could indicate active stabilization, gyroscopes, or reaction wheels, maintaining orientation, despite asymmetric outgassing. Each hypothesis has strengths and weaknesses. Unknown physics is conservative. It doesn't invoke intelligence, but it requires inventing new science without direct evidence. Unknown materials is plausible. The universe contains exotic matter, but it demands that such matter exists in form stable enough to survive interstellar transit and thermal shocking during solar approach. Unknown origin is bold. It explains all observations, but it assumes technology on scales humanity has never encountered. The tension is productive. Science advances by testing hypotheses against data, refining models, eliminating possibilities. As more observations accumulate, some explanations will become untenable. If spectroscopy shows water ice and familiar volatiles, the exotic materials hypothesis weakens. If radar reveals irregular, fractured surfaces, the artificial origin hypothesis weakens. If subsequent images show rotational variation in the beams, the collimation mystery resolves. But what if none of those things happen? What if every new observation deepens the anomaly? What if spectroscopy reveals absorption lines that don't match any known molecule? What if radar shows geometric regularity, inconsistent with natural accretion? What if the beams remain collimated, perfectly parallel, extending millions of kilometers into space without dispersion? Then the scientific community will face a crisis, not a crisis of knowledge. Uncertainty is the natural state of research, but a crisis of frameworks. The tools and concepts developed over centuries to understand comets, asteroids, and planetary formation would be revealed as incomplete, insufficient to explain objects from regimes of age and distance beyond previous experience. This is the threshold where science becomes philosophy. When confronted with data that defies existing models, how should researchers respond? Incremental refinement, adding complexity until the models fit, radical reimagining, abandoning core assumptions, and building new frameworks, or suspension of judgment, acknowledging ignorance until better data arrives. The answer likely involves all three approaches operating in parallel. Some teams will refine comet models, exploring parameter spaces that haven't been fully mapped. Others will propose entirely new formation scenarios, invoking processes that seem unlikely but aren't prohibited by fundamental physics. And still others will advocate for missions and observations that bypass interpretation, gathering raw data in sufficient quantity and quality that the truth becomes undeniable. Loeb represents the third approach. His Galileo project isn't focused on explaining anomalies within existing frameworks. It's focused on collecting data rigorous enough to compel new frameworks. Whether 3I Atlas is natural or artificial, understanding it requires better instruments, closer observations, and higher resolution data than currently available. Speculation, however sophisticated, cannot substitute for measurement. The coming months will be critical. As 3I Atlas moves outward from the Sun, its activity may increase or decrease depending on composition and internal structure. If it contains volatile ices, they will sublime as solar heating penetrates deeper, potentially causing fragmentation or brightening. If it's inert, rock, or metal without volatiles, it will simply recede, fading as reflected sunlight diminishes. The behavior will constrain models. International collaboration is already underway. Observatories in Chile, Hawaii, Spain, and South Africa are dedicating telescope time to tracking the object. Space-based assets, including Hubble and Webb, are scheduling observations. Radio telescopes are attempting to detect emissions in frequencies that might reveal magnetic activity or plasma interactions. The data will be aggregated, cross-referenced, and analyzed by teams from dozens of institutions. This distributed, collaborative approach is modern astronomy's greatest strength. No single observatory or researcher has all the answers, but collectively, leveraging instruments across wavelengths and latitudes, the community can construct a comprehensive picture. Photometry from optical telescopes, spectroscopy from infrared instruments, polarimetry from radio arrays, each dataset adds a dimension, constraining the possibilities. Yet even with global coordination, some questions may remain unanswered. The object's origin, whether natural or artificial, might be undecidable based on remote sensing alone. Without physical samples or close-range imaging, ambiguity persists. And ambiguity in science is uncomfortable. It leaves room for competing narratives, ideological divides, and public confusion. Loeb has faced criticism for publicly advocating hypotheses that many colleagues consider premature. His statements about Oumuamua's possible artificial nature sparked debate that extended beyond academic journals into mainstream media. Some argued that such speculation, without definitive proof, undermines scientific credibility. Others countered that exploring all possibilities, including unlikely ones, is fundamental to the scientific method. The controversy surrounding Oumuamua hasn't been resolved because the object is gone, beyond the reach of follow-up observations. 3I Atlas offers a second chance. If the evidence mounts, if the anomalies persist and intensify, then Loeb's willingness to consider unconventional explanations may be vindicated. If the anomalies fade, explained by mundane processes, then caution will have been justified. But vindication or refutation isn't the point. The point is that the universe has presented a puzzle, and solving it requires intellectual honesty, methodological rigor, and openness to revision. Whether 3I Atlas is a comet, a probe, or something else entirely, understanding it will expand the boundaries of knowledge. Think about what that means for future generations. If ancient artifacts are drifting through the galaxy, detectable with current technology, then humanity stands at the threshold of a new era. Not the era of first contact, signals received and answered, but the era of archaeological discovery. The galaxy as a site of excavation, each star system a potential repository of relics from civilizations long vanished. The implications extend beyond science into culture, philosophy, and existential risk. If intelligence is common, then the great filter, the hypothetical barrier that prevents civilizations from becoming interstellar and long-lived, is either behind us or ahead of us. If it's behind us, then humanity has already passed the most dangerous phase, and the future is open. If it's ahead, then studying ancient artifacts might reveal warning signs, patterns of failure, technologies or ideologies that lead to collapse. 3I Atlas, whether natural or not, is a memento mori from deep time. It reminds us that the universe is old, that stars and worlds have risen and fallen in cycles beyond counting, that everything we build will eventually succumb to entropy. But it also reminds us that structure persists, that information survives, that the past is not entirely lost. If the object is artificial, then somewhere in the thick disk, 10 billion years ago, a civilization existed. They had language, mathematics, engineering. They understood orbital mechanics, thermodynamics, material science. They built something meant to endure, to carry their presence across the eons. And it worked. Against all odds, despite the vastness of space and the cruelty of time, their creation arrived here, intersecting with a young species just beginning to look outward. What message, if any, does it carry? Is it simply a probe, designed to observe and record? Or does it contain data, archives, blueprints, warnings? Without physical access, speculation is futile, but the possibility lingers, a thread of hope, woven through the uncertainty, that we are not alone. That intelligence, once ignited, leaves traces that persist. That the universe, for all its cold indifference, is also a place of connection across time and distance. Or perhaps it's just a comet, an ancient, remarkably durable chunk of ice and rock, shaped by processes we haven't yet fully understood. In that case, the mystery is scientific rather than existential, a challenge to models and theories, not to humanity's place in the cosmos. Either way, the investigation is worth pursuing. The instruments are pointed, the data is accumulating. Scientists across the world are analyzing, debating, refining their hypotheses. The next observations, scheduled for the coming weeks as 3I Atlas crosses Mars's orbit, will provide critical tests. If the collimated beams persist, the anomaly stands. If they disperse or vanish, one explanation prevails. If new features appear, emissions, fragmentations, trajectory changes, the puzzle reshapes. This is science at its most dynamic, responding in real time to phenomena that challenge expectations. It's also science at its most human, driven by curiosity, ambition, and the desire to understand. The researchers tracking 3I Atlas know they're observing something unusual. Whether it's revolutionary or merely surprising won't be clear for months, perhaps years, but the possibility, the sheer possibility, that this object might redefine humanity's understanding of the galaxy is enough to sustain the effort. And if it does, if the data confirms artificial origin, if spectroscopy reveals engineered materials, if radar maps surfaces with geometric precision, then the questions multiply. Who built it? When? Why? Are they still out there, orbiting some dim star in the thick disk, watching for signals from their probes? Or did they vanish eons ago, leaving only these silent emissaries? Humanity would face a choice: to reach out, attempting communication with whatever or whoever sent the object, or to remain silent, studying the artifact without announcing our presence. The debate over messaging extraterrestrial intelligence, MITI, has been contentious precisely because the stakes are unknown. Contact could bring knowledge, alliance, transformation, or it could bring attention from entities indifferent or hostile to humanity's existence. But those questions are premature. Right now, the focus is simpler. Observe, measure, analyze. Determine what 3I Atlas is before speculating on what it means. The scientific method demands evidence before conclusions, data before theory. The process is slow, iterative, sometimes frustrating, but it's also the only reliable path to truth. Read between the lines of the November 9th observation, though, and the urgency is palpable. The collimated beams extending across distances where collimation shouldn't be possible are a flag, a marker, a signal, whether intentional or not, that something about this object is different. Ignoring that signal would be intellectually dishonest. Embracing it without evidence would be scientifically reckless. The balance, acknowledging the anomaly while demanding rigorous proof, is where productive investigation lives. Loeb has walked that line throughout his career. His work on black holes and gravitational lenses is foundational, cited thousands of times, respected universally. His willingness to entertain unconventional ideas, alien probes, interstellar light sails, technological signatures, and astrophysical data has made him controversial but also intellectually vital. Science needs skeptics to maintain rigor. It also needs visionaries to expand possibilities. Loeb occupies the latter role, pushing boundaries, asking uncomfortable questions, refusing to accept "we don't know" as a final answer. Hopkins, meanwhile, represents the statistical approach. His model for dating interstellar objects is elegant, grounded in galactic dynamics and probability theory. It doesn't speculate about composition or origin. It simply takes the trajectory, maps it backward through the Milky Way's structure, and calculates the age distribution most consistent with the path. The result, 7.6 to 14 billion years, is stunning, but it's derived from mathematics, not conjecture. Maslow's contribution, the identification of gravitational ejection as the likely mechanism for the object's interstellar journey, grounds the scenario in known physics. Comets are ejected from planetary systems routinely. Most settle into orbits within the Oort cloud or escape to interstellar space. Over billions of years, a small fraction will encounter other star systems by chance. The probability is low for any individual object, but across the galaxy's 400 billion stars, low-probability events become certainties. Together, these perspectives, Loeb's provocative openness, Hopkins' statistical rigor, Maslow's dynamical modeling, create a framework for understanding 3I Atlas. The object is old, ejected from a distant system, and displaying properties that challenge conventional cometary science. Whether those properties indicate artificial origin or simply reveal gaps in natural models is the question driving current research. The answer will emerge from data. More images, more spectra, more radar echoes. Each observation adds constraints, narrowing the hypothesis space. If the beams remain collimated in subsequent observations, certain natural explanations become untenable. If they vary, others gain support. If spectroscopy reveals familiar molecules, water, carbon monoxide, methane, the exotic materials hypothesis weakens. If it reveals unknowns, the mystery deepens. And if the object simply recedes, fading into the darkness without revealing its secrets, then 3I Atlas joins the list of astronomical enigmas, phenomena observed but not fully understood, data collected but not fully explained. The universe is full of such mysteries, anomalies in cosmic microwave background fluctuations, unexplained dimming in distant stars, fast radio bursts with no identified source. Some will eventually be solved as instruments improve and theories mature. Others may remain perpetually ambiguous, tantalizing hints of processes or structures beyond current comprehension. But this object right now is within reach. The instruments exist. The expertise exists. The opportunity is finite but real. Whether humanity seizes it, whether funding and telescope time and analytical effort are marshaled with sufficient intensity, depends on decisions being made at this moment by administrators, committees, and governments. The history of science suggests that opportunities missed are rarely recovered. The transient nature of astronomical phenomena means that delay equals loss. Oumuamua, the first interstellar visitor, was poorly characterized because detection came too late for optimal follow-up. 2I Borisov was better observed but still left questions unanswered. 3I Atlas could be the first interstellar object studied comprehensively, with multiple instruments across wavelengths, generating data sufficient to resolve ambiguities. Or it could slip away. Another fleeting glimpse of the cosmos's complexity, another reminder that the universe offers puzzles faster than humanity can solve them. The choice is immediate. The window is closing. And the question remains, if the November 9th data are correct, if the collimated beams are real, persistent, and unexplained by natural processes, how deep does this mystery go? And how far is humanity willing to pursue it into the